what matters is that actually Emmanuel did it. His plane was cancelled yesterday, and he's a great hero because he managed to come even so. So it is my pleasure to give the floor to him now, and let's have the last talk of our workshop. Thank you.
Thank you, Jan. It's many heroes, not me, who got me here, including very nice people at different airports. I didn't sleep much. Usually, when I get started, it goes away. But if I'm a bit slow, that's probably the reason. Always good to have an excuse. So I'm going to talk about measures of word frequency or word occurrence through networks of static and dynamic actors. And if I think a few of you have heard me give similar talks, but I think in general it's going to be pretty new. So I've set up some aims to what I want to do in this talk. And I want to start by briefly introducing some concepts from network science. If you already know this, it's going to be boring, but I've tried to make it a little bit non-boring. We'll see. Then I want to introduce a framework for looking at the language environment in a network perspective. And what does that tell us about what the language environment is? At this moment, you don't have any idea what I mean with the language environment. And I hope it becomes clear at some point, but it's a vague term. I will then hopefully convince you at that point that given this framework, it's hard not to notice some oddities in the way we as psycholinguists measure the language environment. And then I will try to demonstrate how measures of word occurrence that we use in psycholinguistics can be understood and related to each other in this framework. It's all very theoretical, no data or simulations. And then comes the big data part, because when preparing for this talk, I went through some of the literature that's been published in the last 20 years, in which you could call big data movement in psycholinguistics. And I will make a collage of things which I find relevant to what I'm trying to explain about these measures. Then, if we have time, we can discuss additional insights that we can derive from this framework, which I find really interesting, but which are not necessarily psycholinguistic, but linguistic in nature. So, I think everybody is familiar with a network, more or less. This is something you can find online. I think I've put a link in the slides, so if you get the slides, you can look at it yourself. This is the full Star Wars universe up to episode 7. I don't know what that is. I feel like I'm a Star Wars enthusiast because I know episode 4 or 5 is the first one, and that's about it. But you see a lot of people from the Star Wars universe here together, and they're connected in some way. And we can zoom in on this. And I'm just going to give you the concepts so that you know what I'm talking about if you don't know this yet. This is only episode 4. So episode 4, A New Hope. I think that's the first one. I'll try to explain what's going on here. So we have nodes, and the nodes in the network represent the individual characters. There are connections, and they connect nodes to each other. And in this case, they are linked to each other if they both speak within the same scene in the script or in the movie. And then we have connection weights, so you can do whatever you want with it. The width of each link represents the frequency of co-occurrence of the two corresponding characters. And you also have a bunch of node characteristics, and the size of each node, for instance, here represents the number of scenes where the character speaks. It's a very modular and dynamic framework. Basically, the only thing you need is nodes and connections, and then you can give all kinds of attributes to these nodes and connections, and you can model a lot of different things with it. I'm not going to model anything with network science today, But Isha, who's over there, you can go to her poster and we'll do some really interesting network science stuff on Chinese characters. So what I want to discuss are some really interesting characteristics of networks which are not known that much in the field. And this is one of those characteristics is flow. And when we build a network, or when we think about a network, we have to think about how things or concepts that we put in the network, how do they flow? Because we can just represent something statically, but typically what's interesting about a network is that some things happen. And what happens to the network and to those things when the network develops. So there are things that we need to take into account. Directionality. How does it flow from one node to another? Degrees of freedom. So in what trajectories is something allowed to follow? Synchronicity. How many things are able to happen at once in the network? And also what happens to things in the network when they travel from one node to the next node. And you can have transfers really simple. If I have something in one node and it goes to the other node, it's not there in the previous node, it's gone. But many processes that we have, and especially in language, and as we will see, you don't have transfer. You have some kind of duplication or mutation. When something moves from one node to another, so when I'm speaking to you, for instance, and I'm node and you are node, it leaves me, but it's still in me. That's a really interesting characteristic of language, but it's mutated somehow. So people who do network science much better than I do have made some kind of famous chart in introductory network science books. And you can see these characteristics here. And you can see some examples of what flow, what kind of things have certain kinds of flows. So for instance, package delivery, if you order something online, it goes to a warehouse and then it goes to another warehouse, etc. And the way it typically goes, it needs to take the shortest path. And it's also transfer. When your package goes from one point to another point, then it's not in the previous point anymore. There are things that are very fascinating, such as STDs. And I hope everybody's familiar with the acronym. So it's basically something that you can give to another person, but when you give it to another person, it doesn't leave you. Right? So you still have it. But the interesting thing is it needs to follow unique nodes and connections that cannot travel the same way around again, because you can't give it to somebody who already has it. So then it doesn't move. And then when you start thinking about language, for instance, you see that it's here. You have things like gossip and Chandler's emotional support, and I like this one, conferences. I'll try to illustrate it a little bit more because I realize I had really good examples of this, Star Warsy. So imagine that you have a package with lightsaber parts and you need to get it to Luke as quickly as possible. This is our network. If you want to get it to Luke as quickly as possible, you can do R2-D2 gives it to C3PO, who gives it to Luke, but you cannot go through Leia because you don't follow the shortest path. You can also say, here, have my old lightsaber, so you can, then it's allowed to go to the same node again, but not reuse the same edges. It's weird if you give the same thing again to the same person. I'm going to go through these quite quickly until we get to the really interesting ones. Another example is lended goods. For instance, in terms of transfer and lended goods, you can keep on lending something out to somebody, such as a lightsaber manual, and we'll get back to why this is an interesting thing. So here's my lightsaber manual, and R2-D2 can give it to C3PO, who can give it to Luke, can give it to Leia, and back to C3PO. That is allowed, for instance. And other things where you reuse the same edges, that's not allowed in this case. Then there are things which are completely free, but they're still transferred, and money is basically that. I can give you money, you can give me the same money back, and it can go anywhere that you want. But most things in language are not like that. They're duplication, or what I would call mutation. So if you're, for instance, transferring galactic credits here, and this is because I really don't have an inspiration I made. I think this is a Bitcoin symbol or something. So it means the transfer happens, but it's no longer there. And I already explained it. If you've got a virus or a disease, for instance, once you give it to somebody, here, it doesn't leave the previous person. And this is an example with an androbovirus. I don't know if you know that. If somebody can answer why Chewbacca doesn't get the virus, it's because he's a Wookiee and so immune to this thing. Then we get to the linguistics examples. Gossip. Have you heard about Leah and Han? And gossip can flow through the same node multiple times, but only if arriving through a connection that has not been used before, right? So if Jan tells Philip that, did you know Emmanuel missed his flight? And he tells Lucica or Mike, it all makes sense until the same person, Jan cannot tell Philip again. But if it arrives at Jan, that's valid. I mean, because, yeah, I knew, but you can tell me because it's gossip. Then there's another thing. I think that I'm taking these examples. Emotional support. We need to defeat the empire, for instance, is something that you can say all the time, right? So it's something that is allowed in every circumstance. And I think much of language is situated in this region. And I also found it, if you know about the Gricean maxims, for instance, that these fit very well. So if somebody is interested in the connection with what is allowed in normal conversation or not, depending on what network flow is allowed, I think it's a really interesting example. I designed the network that I showed you with dynamic actors, and this is what I call it. It's basically things that when they are involved in the network, they change. But when we think about language, we only tend to think about these dynamic actors, right? And I think this is this poetic idea that there is something called natural language. I do not believe that exists in this millennium anymore, and definitely not in our society. But that language is something that happens only in humans, and that only humans participate in the system. And this is, I think, completely wrong. When you think about something like a lightsaber manual, these are things that can have been read by many people. And if you look at Rebel holodrama, for instance, this is actually something that happens in Star Wars. This is something that somebody can watch. But the difference between these static and dynamic actors are not small. It's not just that something is static, it doesn't change, and the other thing does change. And I've listed some of them. So when you think about static nodes, and I know I don't have a perfect definition, but it's definition by criteria. So they're created by dynamic nodes with varying degrees of effort. Sometimes it's really easy to create some static thing that can survive in language. So you can, for instance, send a tweet. Typically, that's quite easy to do. Writing a textbook is probably harder. But the creation of dynamic nodes, that it happens in a different way. So it's a tedious biological process. A static node can immediately start to play a role in the language system. So from the moment it exists in the textbook, it's there, it's done. And it can start transferring or duplicating information in the system. Dynamic nodes, I think mostly humans, slowly increase connectivity in the network. So it takes a long time to have a static dynamic node work. These static nodes, they're immutable. And I find that fascinating. It's like once they're there, they don't change. And they can change a little bit, you know, when something is corrected. But I find it absolutely fascinating that we can still read Shakespeare And it's basically a book or whatever. It's like 400 years and exactly the same thing. And so the difference there is that these static actors have theoretically unlimited lifespan, and they can time travel, and they can also space travel. In contrast to the dynamic nodes, and they can't do that. So the dynamic nodes have biologically limited lifespan. They're also unique. The static nodes, you can clone them, and now cloning is super easy. The static nodes only connect to dynamic nodes. They're unidirectional, and the dynamic nodes connect bidirectionally to dynamic nodes, and unidirectionally typically to static nodes. Typically, static nodes are something that we receive. I'm thinking more about books, but you can also create static nodes. So this is a different thing. And they have varying degrees of connectivity in the network system. Some books, like Harry Potter, are read by a lot of people. Some people have a lot of influence linguistically, others are isolated. And I think the example of PhD theses are always good. Is that somebody's written it, but nobody's read it. So not in our field, not in our field. I read your PhD, I promise. So, and then when we look at what happens in psycholinguistics, and this is kind of the point I want to make, is that we don't treat the network as we should treat it. And now something should become obvious. Psycholinguistics assumes that we can infer how things occur in the language environment, so which the things that happen here, that you can infer this from a bunch of static actors, and you don't have any idea about how they connect to the system at all. This is what we call a corpus. It can be a book corpus, it can be something like movies, anything like that. And that's not the only thing. Psycholinguistics also assumes that there's only one dynamic actor, and that this is the language environment that we have, and that's supposed to represent the language environment for all of our dynamic actors. In other words, this is the corpus that we use to make word frequencies that we use in experiments, and all our participants are the same. So, fine. Now I get to the connection and how you can relate these measures to each other in psycholinguistics. So, static actors again here are red. I've simplified it a little bit. Dynamic actors are blue, and you see that a lot of these static actors have different connections to the dynamic actors. But what we call word frequency, and typically this is corpus word frequency, is this. It's the frequency of static nodes. I don't know if you can read everything clearly. This is, contextual diversity. That's another version. It's a dispersion measure over static nodes. What we don't have, and it would be really interesting, but we don't have it, is this, the connection frequency or the dispersion. So how do those things that we have in those static nodes, how often are they actually experienced by different kinds of dynamic actors? What we do have are these measures, and we don't have them that long, or we forgot that we had them. And it dawned on me while making this presentation. So dispersion in dynamic nodes, that's word prevalence. I don't know if you've heard of word prevalence. It's work that I did with Mark Prisbart and Pavel Mandera. This is basically when you ask like tons of people, do you know this word? Yes or no? And you do that for tens of thousands of words, and then you get really good measures of how many people know a particular word. And so you actually have the dispersion of words through static actors. In the past, people have also asked, or researchers have asked, how frequent do you think this word is? And that was called subjective frequency, and we stopped doing that. Or familiarity. How familiar are you with that word? We still do that with age of acquisition and tons of other variables. So we ask these things, but we stopped asking for subjective frequency and familiarity, except in a few cases. So what I wanted to get to here is that hopefully at this point, it makes sense that these measures are related to these different actors. What I want to get to now is, why am I telling you this? Does any of this matter? And I've anticipated questions that, like, you could ask, like, okay, fine, but do we have any evidence that corpora are not estimating the language environment correctly? Because if they do, now you have all this fancy ideas, but nothing's really going on. And here's something interesting. This is a plot which shows you the relationship between word frequency and lexical decision time in the English Lexicon project. It's a plot we made for a 2012 paper. And these are averages. So this is over all of the participants, and you see something beautiful. The relationship between word frequency and, why did I write it? Means the relationship between word frequency and RT seems very strong and straightforward, right? So you see that even here with very low frequency things, it seems like, yeah, where do you find such a beautiful functional relationship? I think that was very nice, and I think it's also one of the first demonstrations of this beautiful functional relationship. But it hides something, and it hides something that I found perplexing, and I could never explain it well, and it hides this. So this is bins for different word frequencies, and it hides a bunch of different items. This is typically the plot you get. One, you take the reaction time, and I see people nodding because they've seen this. You take the reaction time here, or another measure, and you take the word frequency here. And what you see here are all words which have frequency 1 in your corpus. All of these things are words which have frequency 2 in this corpus. All of these things are words which have frequency 3 in your corpus. And you see that this is insane. I mean, you have in that bin words which on average have a reaction time of 500 milliseconds, as fast as the fastest words, and things which take 3 times as long, and probably have a timeout. So this plot, where you have the averages, masks something weird. And I remember giving a talk in, I think, Marseille at some point, and somebody asked me something about this, and I dismissed it. Yeah, okay, I mean, it's just raw data. The averages are important. But the more I think about this doesn't make sense. And also from a statistical point of view, you should not be able to do a regression on this, because this is heteroscedastic. This is, in fact, we've been doing this for such a long time. And I mean, some experts can tell me, but I don't think that this is allowed in regression to basically say, you can do a regression here and make conclusions about this, because the variance is much different at different points of the distribution. All right. And this is independent of task. That's important. This is lexical decision. You see exactly the same thing in naming. It's also not surprising. And you could say, yeah, but this has something to do with corpus size. If we increase the corpus size, then this disappears. And this could be a really good argument, because these are frequencies from the Brown corpus, and that's only 1 million words. But this is a corpus which is 50 times larger, and you still see it. So you still have bad estimates there. So it's not alleviated by corpus side. So I think that many of you have heard of the Zipfian distribution, or what's called the Zipfian distribution. And that is that the bulk of word types in a corpus are low frequency. So to simplify it, half of the words in the corpus have frequency 1, half of those words have frequency 2, half of those words have frequency 3, and so on. So it's a very long tail of things which occur almost never. That's what happens. And this is the long tail here. So the frequency effect that we see in the low range, so this thing here, it only exists by the grace of the countless low frequency words that appear in corpora. And it's only the average that is estimated correctly. But if you would take a small sample it would be very likely that your frequencies would be off. So you see this through our task, and I love this plot. This is 1951, Hawes and Salomon, visual duration threshold, much better experiment than what we're doing now with the histoscope. 1000 hertz resolution, people are looking at things and they increase the exposure until they can read a word. And this is what you see here. What do you see here? Exactly the same. Right? This is the same plot. Words which occur once in the magazine's corpus of the teacher's handbook that they used at the time, and an R-square of 0.68. Also, kind of the order, or this is a R. The R-square would be probably around 40-ish. All right. Another piece of evidence that corpora don't estimate the language in environment correctly is some research that I did with a PhD student called Rastislav Hronsky. And what we did is we used topic models to estimate the probability of each word in a corpus belonging to a number of particular dimensions. That is really, really bog standard topic modeling. And you can choose how many topics there are, and then the model will discover for you which words in a corpus belong more to a certain topic or not. Then we took RTs for words that participants had responded to, and we call that the training set, and we used them to adjust the weights of each of those topics. And that means more or less, and I'm happy and kind of also sad that Rusty is not here to correct me, that the RTs indicate that participants respond slower or faster than the frequency would predict. And then we had weights for each of those topics. And we used the weights of those topics to transform the frequencies of all of the words in the corpus, not just the ones we had tested on. And we looked at another set of participants with words that were never trained that were never trained on, and we saw that when we had these re-estimated frequencies, they explained with 5 topics it didn't do very well, but with 20 or 80 topics, you explained 7 to 9% more variance. And this is actually an interesting design feature of the British Lexicon Project, because half of the people saw one set of words and half of the people saw the other set of words. And so that means that you can fit on one set and test on the other set. Next question. Isn't this solved by larger corpora? Because if we have larger corpora, perhaps we can estimate the language environment better. And Mark Brisbart and Boris New answered this question in 2009 when they were talking about they introduced the supplex US frequencies. And there's a table in their paper which looks at high frequency words versus low frequency words. I don't know if this is large enough here. And it takes increasingly large parts of the corpus, but it starts with 500,000 words and looks at the amount of variance you can explain by just looking at the frequencies you have until then. And you see that for high frequency words, you're already able to explain 50% of the variance. But low frequency words, only 38. And it stays stable. For the high frequency words, actually 500,000 words is kind of enough to predict the total amount of variance. It really plateaus very quickly. And for low frequency words, you see you need to increase and keeps on increasing. They said 16 million words. And then there's a problem, and it reminds me of another person who does this quite often, but this is in relation to age and old people and how old they are. And this is in relation to the frequencies. These are not really low frequency words. They're pretty high frequency words. So this is on a small corpus. This is less than 10 per million, which is on the border of low and high frequency, according to what we did later in the Supplex UK paper. So even for words which have relatively mid frequency, you're not doing well. And so to me, this is not a great result. Another paper by Heragdelen and Marelli shows that explained variance keeps on increasing steeply up to 100 million words. And this is on the Rovereto Twitter corpus. So you use word frequencies from the Rovereto Twitter corpus. Brilliant word frequency. They're great. I would advise you to look at them. But you see 10 million, 100 million, 1 billion, and it keeps on going up until there. So is this really solved by corpus size? You see it flattening out. There's another problem here, and this is something that we can solve, and that is that the selection of words, even in megastudies, is a selection. And by design, you're already dealing with a relatively known part of the frequency spectrum. And the only thing you're doing is really, can we discover this word somewhere in the corpus? And the larger the corpus gets, the more likely you are to do this. These are frequency trajectories. I'm going to skip over that. The next question, you could say, oh, but you don't have any alternative, right? Aren't all of these frequency measures somehow correlated? And there's an important frequency measure called contextual diversity, and perhaps this could help us, because contextual diversity, as James Edelman and others have argued, is very different from frequency. And I agree. Theoretically, the concept is different from frequency. And so how do you get to this counter in your head, or the contextual weight of a word is very different. But when you look at the data, this is the relationship between contextual diversity and word frequency for all the words in the British Lexicon Project. And you see it has a very nice curve here. They're very similar measures. And you can straighten this out. And then the correlation between word frequency and contextual diversity is 0.98. And I have to say, I like the idea of contextual diversity, and I think that there's something really theoretically interesting behind it. But when you measure it on a corpus, it's not that different from frequency. Right? And so what I'm doing here to adjust this is to basically say, if you have a word of this frequency, in how many documents would you expect it to appear? And then I have my simulated contextual diversity measure. So the correlation is 0.98. Let's take another measure. Frequency and word prevalence. I've talked about word prevalence before. Word prevalence is the amount of, or the proportion of people in a population who say that they know a word. And we have, because of all kinds of crowdsourcing studies, really large sets of prevalence data for many different languages. This is for Dutch. This is the first one that we did. And as I said before, the frequency is the sum of counts on static nodes, books, movies, things which don't change. And prevalence is the dispersion in dynamic actors. What you see here is in contrast to, so remember this plot. This is the relationship between frequency and contextual diversity. This is the relationship between frequency and prevalence. These are not the same measures at all. And what you need to get from this is, you see this line again, and we've seen this line before. These are all words which have frequency 1 in the corpus that we used. And look at the range of prevalence. This is Z transformed, so -2 means almost nobody knows it. +2 means almost everybody knows it. So for words that occur once in this corpus, some of them are known by absolutely everyone, and some of them are known by absolutely no one. And here you have words with very high prevalence, so everybody knows them, but they have very varying frequencies. So we are doing something very different by looking at a corpus and asking people about this. And does this matter? I don't have graphs on this, and I can show them later. But we've shown in several papers that prevalence explains the same or more variance than frequency, and because it's not so correlated with it, it's not that it's one or the other. And just to show you the difference in correlation, this is the correlation between frequency and contextual diversity at 0.98. the correlation between frequency and prevalence is 0.35. It's not the same measure. So depending on how we query the language environment, we get very, very different things. Does it affect research operations? So if it doesn't affect your research operations, you shouldn't worry about this. The frequency effect on average is extremely large and linear in the low frequency range. So here, what we saw on average is that you have an effect of 300 milliseconds that doesn't exist anywhere. Anywhere in the literature, you never have such an enormous effect between one group and another group. But you have a 300 millisecond effect between 1 per 100 million and 100 per million frequency. And every time you multiply the frequency times 10, that corresponds to a 60 millisecond difference. Now, if you're doing a small experiment or even a small virtual experiment with things from a mega study, it's very likely that you may attribute something that is actually frequency effect to something in your, that is explained by another, something, you're attributing something to another variable that is actually frequency effect. Yeah. So the smaller the set of words is, the higher the probability that there is a mismatch between the corpus frequencies and what you could call the true environment frequencies for a particular participant. This is also, I think, an interesting plot about the relationship between frequency and prevalence. And what we've done here is taken different ranges of the frequency variable. So the frequency we know, and we're looking at very low frequencies up to very high frequencies, and we've split that into 50 different bins. And we look at how much the different variables explain in the different bins. Eta squared is a measure of effect size. So on the same scale as R squared. And you see that within small frequency windows, frequency doesn't explain a lot until quite high frequency, but prevalence explains quite a lot all through the range. If you do it the other way around and you divide prevalence in 50 bins, you basically see that frequency explains something for words which have very low prevalence, and that makes complete sense. Their frequency is something that can distinguish between things that nobody knows. Fine, this is interesting. But prevalence starts out not explaining, well, it explains a lot, and it explains more and more and more as words become more known. Does it affect research operations? Again, I'm going to show you this plot about the topic models, and these topic models adjustments based on reaction times, they suggest that some parts of the lexicon are structurally under or overestimated. Remember, what these topics are just things that you can talk about in conversation, and they're computationally estimated. But when we do that, we see that when we adjust them for reaction times, that these topics have different weights. And that means that in your corpora, in the corpora that you use, they're not balanced across topics, or you're not measuring the environment correctly. I'm getting back to my aims. I already discussed this, but I like to have them at the end again. So what I wanted to do is introduce some concept of the network science, introduce this framework, convince you of some things, and then talk a lot about, show you a lot of plots from different papers, which I maybe went over too quickly. But to explain all of this is, I like to show a lot of things, so it's difficult for me to choose. And I would consider, and perhaps also in connection with this workshop, that all of these plots I'm showing you are examples of what we're doing with big data in psycholinguistics. So all of these things at different points of the last 20 years are investigating effects in psycholinguistics through very large amounts of data. So I have a bunch of discussion points, but I think it's you need to select one of them. No, I think we can also go to questions, and perhaps I can show you some other slides later.
Thank you very much for a very interesting talk. I think there is a lot to discuss, and we have some time here, and then we can continue somewhere else. So are there any questions now? If you can wait for the mic, because of the...
Thank you, Emmanuel, for the beautiful talk. I was just thinking, when you were connecting frequency and contextual distinctiveness, diversity, did you try to maybe somehow constrain one on the other to see if the word has contextual distinctiveness as predicted by its frequency?
Yeah. So I think it's a very good question. You can actually see that. So here, when you do that, this is the line where this is the case. So this line would be the if you would exactly predict the contextual diversity from frequency, well, it would follow this thing, right? And these things, everything that's here is less diverse than its context would predict if the diversity were uniform. So this is the line of uniform diversity, right? This is what you would have, is the maximal diversity that you can have for a word with a particular frequency. Everything that's to the left of this line here has less diversity than predicted by its frequency.
Did you look into it to compare?
No, I think that this was I remember that we looked at which words these are, and you can say something about them. But in this case, it was an exercise in showing that they're not that dissimilar. Yeah.
Because then this measure might be more informative, like corrected contextual diversity. Yeah. Then it would actually be informative.
You could do all kinds of fancy adjustments for the measures. Absolutely. Yeah.
Thank you.
So any more questions right now? Erin, you wanted to? Yeah.
All right. So the big thing that people are putting under review now is using large language models to estimate these different things, because people are annoying to measure, as you're aware. So do you think that that captures better, or we're just still fooling ourselves because they're trained on very large corpora that don't best estimate dynamic actors?
So I think this is something I'm looking at also with my PhD students. And the idea is that the corpora are not the language environment. And what you can do is to make a language model based on the corpora and then produce things based on the language model. And then that's basically what you have, right? So these are the estimates based on large language models. I don't think that is silly, but my PhD student, who is much more mathematically inclined than me, tells me that there are certain results in the literature that say that these frequencies should stochastically approach exactly the same values. I don't know how much that counts for the very sophisticated language models that we have now, but it would depend on how much you sample. So if you have smaller sample, you would typically get things which have less rich vocabulary. It might surprise you, but large language models have much less rich vocabulary than people do. They sound more eloquent, but they use less words. There's different words, unique words.
All right. Any other questions? Is there a question or no? We're just raising. Okay, Erin again.
Just because I'm still mad about Wuggy. I'm kidding. So I guess the question, if you were to use network science for this, could you take individual data per se and model individual networks and then create sort of an average, because we mostly talk about average humans, but could you average those networks to think better about how the dynamic and static
I think
interplay?
these topic models or similar methods, what you could do is find ways to estimate how a specific subpopulation or a specific set of participants differs from the average that you would get from a very large corpus, and try to estimate. I only don't know how relevant that is to psycholinguistic research where you want to make inferences. It would be more, I think, interesting as a goal by itself to see if you can do it. But what I do think, and this last thing, is that we have unfairly downplayed the importance of subjective measures such as subjective frequency and familiarity. And one of the reasons that this is the case is that when these measures were tested, for instance, in the 80s, people didn't like them because you couldn't see the effects of familiarity. But when you look at the effect of familiarity on a mega study, boom, it's there. And the effect of subjective frequency, these things are there. So it's perhaps useful to look at subjective frequencies again for particular groups, especially if you're using the same stimuli again and again and again. Might be useful to look at that in your particular subgroup. Yeah.
Okay. Perhaps one last question. Anyone?
Can I show something?
You have more slides. Yeah, Danny.
So here's an interesting thing, and this is not psycholinguistics, but when you look at a network with dynamic and static actors, you need to think about, like, was this always the case? And the funny thing is, like, we don't have natural language. We estimate the things based on books, but those books have not always been there, and literacy also has not been there. But we know at a certain point in time that there must have been a massive expanse in static actors in the network. And that is the case when the metal set printing is invented. And there's a very funny thing, and correlation is not causation. But I looked at the literacy rates from 1475 to 2022 in relationship to certain events. And you probably know that the book printing started in Germany, Netherlands, Belgium, Western Europe. And you see very quickly, massively increasing literacy rates from the moment that these static actors start expanding, probably because there's something to read, and people didn't have access to book manuscripts before that. And in other places in the world, you don't see it that much. And there are interesting cases here. This is the world in general. So this is certain parts of Europe. This is the world in general. And this one is India. And this has absolutely nothing to do with India as such, but with the fact that I think it took until 1806 before people were able or were pressing books in Sanskrit, because the metal types were not set yet. And so you were not able to produce static actors in the language that people know. Not on this, but you see also effects of literacy on when you have religious reasons to not have books spread. And you see this in the Ottoman Empire, for instance, where this is very, very developed, but you see that the literacy rate starts increasing much later than in Western Europe. I don't know if it exactly coincides with the printing press. So this is not just about psycholinguistics, but more in general. I think it's fascinating that when you think about the composition of actors in a network, they have consequences. And then, of course, I thought somebody would ask this about artificial dynamic nodes that we have now, and these are the things that we interact with ChatGPT, etc. They also have really interesting characteristics, and we think that they are dynamic nodes, but they're not. But they generate a lot of other static actors, and yeah, this may be problematic. All right, thank you very much.